Hi everyone, today a video on the Thermodynamics series looking at enthalpy changes and Born-Haber cycles. So firstly, if you're not so confident with enthalpy changes and the kind of basic energetics and thermochemistry, I recommend going to my series of videos on that topic, on the energetics topic, where I go into what is an enthalpy change, how can we measure it, and how can we calculate it using enthalpy changes of formation, combustion, bond enthalpy values, and Hess's law cycles. Now, I'm not going to have a chance to go back into all of those details again, but a couple of key things that we really need to remember is that an enthalpy change is just a heat change at constant pressure. So it's simply an energy change but measured at constant pressure. And we often talk about standard enthalpies. That means that we are measuring our enthalpy change at a set of standard conditions, because remember, the enthalpy change depends on, firstly, the amount of substance we have, but also on the conditions that we have, the temperature, the pressure, and the concentration. And so standard conditions we define to be 100 kilopascal pressure, 298 Kelvin temperature, and 1 mole per decimeter cubed if it's a solution. Now, we also talk about the standard states of reactants and products. The standard state is how that reactant or product exists under those standard conditions. So essentially, if you were to have that in front of you at room temperature and pressure, what would it look like? Would it be a solid, a liquid, or a gas? And so, for example, carbon at 25 degrees Celsius at room temperature and pressure is a solid, and we use the graphite allotrope of that. If we take things like hydrogen, hydrogen actually doesn't exist at room temperature and pressure as just a hydrogen atom. It exists as an H2 molecule. H2 is a gas. Same thing for something like fluorine, F2 is a gas. Oxygen exists as O2 as a gas. Nitrogen is N2 as a gas. So it's how we actually find these things at room temperature and pressure. So, for example, it's not an oxygen atom on its own, it's O2 as a molecule of gas. Now, before we get on to looking at Born-Haber cycles, which are really just slightly bigger versions of Hess's law cycles, remember that Hess's law stated that the enthalpy change was independent of the route that we took. A Born-Haber cycle essentially is just a larger version of that. We need to go through a number of definitions. And again, as I said in those previous videos on the energetics series, learning definitions can seem a bit dry, but for one, they're very easy marks in an exam if you get asked them, if you can just learn them. And secondly, the definitions, more so than when we did Hess's law cycles, are really, really important in terms of helping us actually calculate values, because it can remind us what we're actually calculating. And so the first few are going to be ones that we hopefully remember from the energetics series. We have the standard molar enthalpy of formation, delta HF. That symbol there that looks a bit like a tube sign, it's called a plimsoll symbol. It's superscript, goes sort of to the top of the H. That's just representing the standard conditions, and it's F for formation, so delta HF standard. And this is the enthalpy change when 1 mole of a compound is formed from its constituent elements under standard conditions or reactants and products in the standard states. So the really key takeaways from this is that we have our constituent elements under standard conditions, reactants and products in standard states, and the key thing is it's when 1 mole of a compound is formed, 1 mole. And so an example might be the formation of water, H2O. The constituent elements are hydrogen and oxygen, but we have to think about how we find them under standard conditions. We don't find hydrogen and oxygen just as hydrogen and oxygen atoms. We find them as these diatomic molecules, so H2 gas and O2 gas. And so if we write this balanced equation, H2 gas plus a half O2 gas goes to H2O as a liquid. Remember that when we write out our thermochemical equations, it's always really important to remember to put the state symbols in, because the state can affect the enthalpy change. And so you can see that the formation enthalpy is minus 286 kilojoules per mole. Now, enthalpy changes of formation are always negative. Think about it, we are forming these molecules from their constituent elements, and when we form bonds, remember that that's an exothermic, that's a heat being given out because bonds are being formed. If bonds are being broken, then that's an endothermic, a positive enthalpy change because heat is being taken in. But enthalpy changes of formation, always negative. And the standard enthalpy of formation of an element is by definition 0. The way to think about this is that you can't form something that's already been formed. So the standard enthalpy of formation of oxygen, for example, well, oxygen exists, it's a standard enthalpy, so oxygen exists in its standard state as O2 as a gas. and so therefore you can't form O2 as a gas from O2 as a gas. It already exists like that. So the standard enthalpy of formation of an element, by definition, is 0. The next one is the standard enthalpy of atomization. So this is given the symbol delta H at AT for atomization. And this is the enthalpy change which accompanies the formation of 1 mole of gaseous atoms from the element in its standard state under standard conditions. Now that may seem a bit arbitrary, so let's look at a few examples. The two key takeaway messages here is that it accompanies the formation of 1 mole of gaseous atoms, so it has to make a gaseous atom, and it makes it from the element in its standard state. So let's say we're atomizing bromine. Bromine exists in its standard state, not as a bromine atom, of course, but as a bromine molecule, Br2, that diatomic. And so to atomize it, we have the formation of 1 mole of gaseous atoms, so we're going to be forming 1 mole of Br as an atom. For that to happen, we have to have a half B2 to start from. So we form it from the element in its standard state, Br2, as a gas. We're forming 1 mole of gaseous atoms, so that's 1 mole of just Br as a gas. And so therefore our equation for this is a half Br2 going to Br. So you can see that we've not actually changed the state of this, they're both gas, but we've gone from essentially a half Br2 to Br. So it looks the same because a half Br2 you can think of as just being a bromine atom. But here we're saying we've actually gone from the element in its standard state to just a mole of gaseous atoms. The same thing is true of chlorine. Chlorine exists in the standard state as Cl2, as a gas. Our atomization enthalpy would be when we turn that element in the standard state into 1 mole of gaseous atoms. So 1 mole of Cl atoms, so just Cl as a gas, and therefore to balance our equation up, a half Cl2. And one of the reasons this is so important to remember the definition is quite often when we do Born-Haber cycles, we have to think about how many moles of stuff we have and the ratios that we have. And so it's really important to remember that the atomization enthalpy is for the formation of 1 mole of gaseous atoms. A final example would be magnesium. Now magnesium already exists as just Mg on its own. However, the standard state of magnesium is a solid. And so our atomization for magnesium would be magnesium solid turning into magnesium gas. So here we haven't actually had to change the formula of our element in the standard state. We've just had to change the state. So the key thing is to notice how it's given in terms of 1 mole of chlorine or bromine atoms, not 1 mole of molecules, because the definition, this is why it's important to know the definition is for the formation of 1 mole of gaseous atoms from the element. Now atomization enthalpies will always be positive because you have to put energy in to convert through a change of state. So if we're converting a solid to a liquid or a liquid to a gas, this is an endothermic change. We have to put energy in to do that, a positive enthalpy change, because we have to break intermolecular forces. Or potentially even within a molecule, we're breaking covalent bonds. And this is an endothermic process. We have to put energy in to break bonds. The next is the enthalpy change of first ionization, delta Hi. This is the enthalpy change when 1 mole of gaseous atoms are converted into a mole of gaseous ions, each with a single positive charge under standard conditions. There's quite a lot to take in here. The key thing is that it's a mole of gaseous atoms, 1 mole, gaseous atoms, and when we convert those gaseous atoms into 1 mole of gaseous ions, each with a positive charge. So we're just simply ionizing it, removing 1 electron, but everything is in the gaseous state, and it's for 1 mole. So the example would be sodium, going to sodium plus. Notice how they're both gases, and our electron as well. Now enthalpy changes of ionization are always positive, endothermic, we've taken heat energy in. And that's because we have to actually rip off our electron, knock off this electron from that molecule. Now remember that there's electrostatic attraction. While the overall sodium atom is neutral, there is electrostatic attraction between the electrons that are negatively charged and the protons in the nucleus that are positively charged. And so therefore, because we have to break this electrostatic attraction, we have to put energy in to do that, to remove the electron. So endothermic, a positive enthalpy change value. There's also something called the second ionization energy enthalpy change. And this refers to the loss of 1 mole of electrons from a mole of singly positively charged gaseous ions to form 1 mole of gaseous 2+ ions. So simply what this means is we're going to start from the 1+ ion and then do another ionisation energy, technically the second ionisation energy. And so that here is our sodium plus as a gas. Again, it still has to be gaseous. Sodium gaseous plus going to sodium 2+ gaseous plus an electron. And you can see here again it's positive. Here it's far, far more positive because if you remember the electronic structure of sodium, we lose 1 electron, we form that very stable noble gas configuration of we have our 8 electrons in our outer shell. To remove 1 more takes so much more energy because we have to break that 8 electron octet rule. We then have something called the first electron affinity. So the first electron affinity is the enthalpy change when 1 mole of gaseous atoms is converted into a mole of gaseous ions, each that has a -1 charge under standard conditions. So electron affinity is essentially the opposite of ionisation energy. We're not knocking an electron off, we're technically adding an electron. So we start off with our gaseous atoms, 1 mole again of gaseous atoms, and we convert it into a mole of gaseous ions that have a -1 charge under standard conditions. So an example would be to take oxygen as a gas. Now notice here that we have, again, it's why it's important to remember the definitions here. It's not our enthalpy change when 1 mole of our atoms or elements in our standard states. It's just when 1 mole of gaseous atoms. So we don't have to write this as O2. We're not talking about when 1 mole of an element. We're talking about when 1 mole of gaseous atoms are converted. So it's just simply O as a gas. Then we add an electron, and this creates the O- anion. That's a gas as well. And so we give it the symbol delta HEA. And enthalpy changes for first electron affinities are always negative. Now this is because we're adding an electron. And again, while overall the molecule is neutral, remember the nucleus has all this positive charge. And so we have electrostatic attraction between the electron that we're putting in and the nucleus that's already there. So because we have electrostatic attraction, it's exothermic. You can imagine it being like a favourable process like forming a bond, and therefore it's exothermic. Heat is given out in it, therefore it's a negative enthalpy change. And this leads to a very general rule that typically if we have to take heat energy in, it's endothermic. If we give heat energy out, it's exothermic. But we can also think about it in terms of attractive and repulsive processes. If it's an attractive process, for example, ions of opposite charge, this is also an exothermic heat energy given out. We don't have to force that to happen, it will naturally happen. However, if we have a repulsive process, for example, like charges, so 2 negative charges together, that's a repulsive process, that's endothermic. We have to actually, they will repel naturally, we have to force them together by putting energy in. And so this equation there is for the first electron affinity. Like the ionisation energy, you have the first ionisation energy, then a second ionisation energy, and so on. Here we have the first electron affinity, we can have the second electron affinity, and so on and so forth. And again, note that it refers to single gaseous atoms, not oxygen molecules. We then have a second electron affinity. This is giving the symbol delta HEA, sometimes delta HEA second, just to distinguish it. And this is the enthalpy change when we take 1 mole of electrons and we add them to 1 mole of gaseous ions, each that have a -1 charge, forming 1 mole of gaseous ions, each with a -2 charge under standard conditions. And so again, it seems like a fairly wordy definition, but essentially what we're saying is that everything is gaseous, everything is 1 mole of something, and we simply start off with our negative ion with 1- charge, add an electron to make the 2- ion. And so carrying on with the oxygen example, we have our O- as a gas. We add our electron and we create our O2-, our oxide anion, also as a gas. Now, this is the key distinction to make. If you take one thing away from this video, let it be this. Enthalpy changes of second electron affinities are always positive. They're endothermic, heat's been taken in. So first electron affinities are negative, second electron affinities are positive. This differs from ionisation energy. For the first, the second, the third, whatever ionisation energy is, these are always positive values, endothermic. We have to put energy in to take the electrons away. And typically, as we go up from first to second to third to fourth and so on, the values become higher and higher because it takes far more energy to break away an electron from a positive ion than it does from an electron from a neutral species, essentially. Electron affinity is different, though. First electron affinity is negative. We're adding an electron in. We have our positively charged nucleus. That's an attractive process, so exothermic energy is released. However, the second electron affinity is positive. And this is because we're adding an electron, but now not to a neutral species, but to a negatively charged ion anyway. And so we're putting a negative charge next to a negative charge. Massive repulsion. And so because it's a repulsive process, we have to put energy in to force them together to make it happen. And therefore it's an endothermic process, and heat has to be taken in. This will be really important when we come to look at drawing out Born-Haber cycles. The next is the lattice formation enthalpy, delta HL. This is the standard enthalpy change when 1 mole of a solid ionic compound is formed from its gaseous ions. So this sounds very theoretical and a bit odd that you take 2 gaseous ions and they come together and magically form an ionic solid, but that's what the definition is. And so the example would be to form sodium chloride, the ionic solid. So you take the sodium ion as a gas, the chloride anion as a gas, and form sodium chloride as a solid. So gaseous ions, 1 mole of gaseous ions forms 1 mole of our solid compound, our solid ionic compound. Now, lattice enthalpy can either be lattice formation enthalpy or lattice dissociation enthalpy. Enthalpy changes of lattice formation, that is forming the ionic compound, like is shown at the equation at the top, they're always negative. Exothermic reactions where heat energy is given out, because essentially we are forming bonds to make that ionic compound. We've got the ions, we form the ionic bonds to make the compound. Making bonds, energy is released, it's exothermic. The opposite process is called the enthalpy of lattice dissociation. So this is the reverse equation, taking our solid ionic compound, breaking it up into gaseous ions. So the definition of lattice dissociation is when 1 mole of a solid ionic compound dissociates into its gaseous ions. This will always be the same number as the lattice formation, but the opposite sign, positive sign, because we're having to put energy in to break bonds. So always make sure that you're careful with, if you're writing a definition, make sure you either go for formation or dissociation. And if you're dealing with it in a calculation, as we'll see with Born-Haber cycles, make sure you use the right one. Then we have enthalpy change of hydration, delta HYD, hydration. This is the enthalpy change when water molecules surround 1 mole of gaseous ions. So if we think about what happens when we actually have ions in solution, they don't just exist as, for example, the sodium ion on its own. If it's in aqueous solution in water, the water molecules crowd around the sodium cation, and they also crowd around the chloride anion. And we end up creating what are these called, essentially it's an intermolecular force, it's called an ion dipole force, because we have our ion and part of the dipole on the hydrogen, the water interacting together. So remember, our dipole is our polar bonds, our electronegativity. And so we have these dipoles in water because we have a much more electronegative oxygen than the hydrogen. So delta negative on the oxygen, delta positive on the hydrogen. We have our dipole always going from positive to negative towards the oxygens. And so we have these ion dipole forces created. And so you can see that if we take our ions in the water, that we have to have electrostatic attraction. That's the favourable process. And so it is actually the oxygen atoms that are interacting with the sodium cation, and it is the hydrogen atoms that are interacting with the chloride anion. That's because our oxygen is delta negative, so matches with the positive sodium. The chloride anion is negative, and that matches with the delta positive hydrogens. So essentially it's the same water molecules, if you like, just rotated one way or the other. And so some examples of writing the actual equations, it's when, again, gaseous ions, so we have to start with either the sodium plus or the chloride minus gaseous ions. And typically we can just write this as plus AQ to denote that we are in aqueous solution in water. And then that ends up forming Na plus in the aqueous state now. And these enthalpy changes of hydration will always be negative because we're forming these ion dipole intermolecular forces. It's kind of akin to making a bond. That's a favourable process to electrostatic attraction, and therefore these are exothermic negative enthalpy changes where we've given heat energy out. And the next one here is our enthalpy change of solution. This is slightly different to our enthalpy change of hydration. This is the standard enthalpy change when 1 mole of solute, that's 1 mole of our solid essentially, dissolves completely in sufficient solvent to form a solution in which the molecules or ions are far enough apart not to interact with each other. So essentially it's to dissolve up your solid compound in so much solvent, in so much water, that essentially we form an infinitely dilute solution, that our molecules or ions are not interacting, they're so far apart. So an example here would be to take NaCl, dissolve it up, we can write it as plus AQ, and make the sodium aqueous ion and the chloride aqueous ion. Now it's kind of related to, but not quite the same as our enthalpy change of hydration. The enthalpy change of hydration was taking our gaseous ions and then writing that with plus AQ and making our aqueous ion, but it was the individual ions. So we had one for the sodium and one for the chloride ions. The enthalpy change of solution is to take the ionic compound that we're dealing with, in this case the sodium chloride, and to imagine dissolving that all up in one go. And so we end up we start with our solid ionic compound and we make our sodium and our chloride ions that are aqueous. Now, enthalpy changes of solution are always positive, endothermic, heat will be taken in, because bonds are always being broken. We are having to break apart the sodium chloride ionic salt and to dissolve it up. We have to actually physically break the ionic bonds. And while, of course, when we make our sodium and chloride ions, they will be surrounded by the water molecules like we saw on the previous slide, essentially it's the formation of some intermolecular forces versus the breaking of ionic bonds. And the breaking of the ionic bonds is always going to be a larger value because we're actually breaking physical ionic bonds rather than weaker intermolecular forces. So enthalpy changes of solution, positive. We then have our mean bond enthalpy. We talked about this in the energetics series as well, or mean bond dissociation enthalpy. This is the enthalpy change when 1 mole of gaseous molecules each breaks a covalent bond to form 2 free radicals, so what we call a homolytic cleavage, 1 electron goes to each, averaged over a range of compounds. So the key things to take away is that it's gaseous molecules to form these gaseous atoms, these gaseous free radicals essentially, breaking covalent bonds. So you'll never find a mean bond enthalpy for an ionic bond or a metallic bond. It has to be a covalent bond. And the key thing, because it's a mean bond enthalpy, it's the actual value of this bond in lots of compounds averaged over all the compounds you've taken the values from. So the example would be taking methane, CH4, breaking those 4 CH bonds to produce a carbon atom and 4 hydrogen atoms. This is all gaseous, so CH4 as a gas goes to carbon as a gas plus 4 hydrogen as a gas. These are technically free radicals, which I'm not going to show because essentially you're ending up with the normal carbon and normal hydrogen atoms. And so we then have our dissociation here as being plus 1664. That's for the whole molecule though, so our average CH bond enthalpy is a quarter of that because there are 4 CH bonds that we've broken. We want it for one of those bonds, so we divide it by 4 to get plus 416 kilojoules per mole. Enthalpy changes of bond dissociation are always positive, endothermic, because we have to take heat energy in to break the bonds. So this then leads us on to Born-Haber cycles. Now, Born-Haber cycle is a thermochemical cycle, like a Hess's law cycle was, but it includes all of the enthalpy changes for the formation of an ionic compound. So for our Hess's law cycles, we were often thinking about using enthalpy changes of formation, enthalpy changes of combustion, to work out the enthalpy change of a particular reaction. Born-Haber cycles are a specific type of thermochemical cycle that deal with the formation of ionic compounds. Essentially, it's just an application of Hess's law. Remember that Hess's law stated that the overall enthalpy change was independent of the route that we go. It doesn't matter whether we go in the Hess's law cycle, it didn't matter if we went straight across the top reaction arrow or whether we went sort of through the sort of more triangular down one arrow and up the other. As long as the overall enthalpy, as long as we start from the same point and end at the same point, it doesn't matter which route we go. The enthalpy change will be the same. And so here I've drawn the Born-Haber cycle for sodium chloride. I'm going to go through how to form this. So we have to use all of the steps that we've considered, or at least most of the steps that we've considered from these definitions that we've just talked about for the past 20 or so minutes. So we have our atomization, we have our ionization, electron affinity formation, and lattice enthalpy of formation, enthalpy changes. So the way to start off by doing this is to always start by putting the elements in their standard states in first. That's our 0 point by definition. We said that our elements in their standard states have enthalpies of 0 by definition. So if we think about sodium chloride, what's our elements in their standard states? Well, it's sodium as a solid and it's chlorine as a gas, but remember in the standard state it's Cl2. Think about the formula. The really key thing to do for Born-Haber cycles is to always think about the formula of the compound we're dealing with. So it's sodium chloride, NaCl. We only need one chlorine atom. So actually the standard state, if you like, of the elements in our sodium chloride are sodium as a solid and then a half Cl2 as a gas. So then we always have to consider the equations and consider the definitions to help with the stoichiometry and the signs. Most of the errors in making these actually come from not knowing the definitions well enough and therefore getting the actual equations that you write on each of the steps wrong, or with a lack of care of the signs. And again, that really comes from the definition, because if you understand the definition, you understand exactly what the process is, and therefore you'll understand exactly whether you're making or breaking bonds, whether it's attractive or repulsive, and therefore whether it's positive or negative. So we said that, remember, that if we are forming bonds, that releases energy. That's an exothermic reaction. That's negative in terms of enthalpy, or we could say an attractive process, an attractive force like electrostatic attraction was also exothermic. But because it's negative, what that means is that when we draw arrows between the various steps, that they go down. Likewise, if it's positive, an endothermic process, this could be breaking bonds, we have to put energy into break bonds, or a repulsive process where we have to put energy into force things together, that's a positive enthalpy change, and hence the arrows go up. So the way that I draw Born-Haber cycles is as follows, and I go step by step in thinking about how do we make our ionic compound. So the first one that I always consider is the one that we probably know the best from even the energetics series, our enthalpy change of formation. So if we look for our equation here, it's the fifth one down. It's our sodium as a solid plus a half Cl2 as a gas to sodium chloride as a solid. Remember, the formation is the enthalpy change of the formation of 1 mole of our compound from the elements in their standard states under standard conditions. So this is why it's useful to put the elements in standard states in first as the 0 mark, because then we can put this formation enthalpy in. And so we simply draw an arrow. It's a negative enthalpy change. It's exothermic because we're making bonds. And so I'm going to draw, first of all, an arrow that goes down. So that's starting from the point that I've labelled 6 and going down. And that's our NaCl. And the actual ionic compound I always draw as a really big line right at the bottom. I'm now going to start working my way around the other way of the cycle. So if I think about actually how I make my ionic compound, the series of steps that I have to do are I have to atomize both of my elements, in this case, the sodium and the chlorine. I have to ionize my sodium to turn it into a sodium positive cation. I need to do the electron affinity for my chlorine to turn it into a chloride anion. That's our formation of our ions. And then to get the ions to form the actual ionic compound, I need to do the lattice enthalpy of formation. And so I always do it as this series of steps in this order. So the first thing I'm going to think about doing is atomizing the sodium. Remember that our atomization was to essentially turn the element in its standard state into 1 mole of gaseous atoms. And so for sodium, well, it's already 1 mole, but it's in standard state as sodium solid. So atomizing it turns it into 1 mole of sodium gaseous atoms. And so you can see here, the key thing that I've changed in every equation I've highlighted in red. The actual half Cl2 as a gas at this point hasn't changed. I'm also then going to just write on my enthalpy change, which I've shown here in blue. And so I put the delta H of atomization is plus 108 kilojoules per mole. And I put an arrow going up. Then I have I need to atomize my chlorine. So in this case, remember, it turns it into 1 mole of gaseous atoms. So I'm going to have Cl as a gas. And this again is why it's important to start from the half Cl2, because half Cl2 essentially is the same as Cl. But here we're going from a half Cl2 molecules as a gas to 1 mole of chlorine atoms as a gas. And again, this is why it's important to remember the actual definitions and the stoichiometries it refers to. we always have to consider whether our enthalpy change needs to be times by 2 if we have 2 lots of an element, or if it's 2 successive enthalpy changes that have different numbers. And so we'll see some examples where potentially we need 2 chlorine atoms. For example, if we're making magnesium chloride, MgCl2, we need 2 chlorine atoms. And so based on our atomization enthalpy, we'd have to multiply that by 2, because our atomization only refers to forming 1 mole of chlorine atoms. We might need 2. In this case, though, we only need 1 mole of chlorine atoms, therefore we can just write the atomization on, arrow going up. Then I think about ionizing my sodium. So that's, again, an endothermic change here, so an arrow going up. And we end up forming a sodium plus gaseous ion. Remember that our ionization, everything has to be gaseous. So that's why it's important to do your atomization first, and then do the ionization. So our equation now becomes Na plus as a gas, an electron, plus chlorine atom as a gas. Then I need to turn my chlorine atom into a chloride ion, so that's the electron affinity. Remember the first electron affinity was exothermic, the second electron affinity was endothermic because of the attractive versus repulsive processes. Here we only need a 1 minus ion, so we just have our first electron affinity, exothermic because it's an attractive process, arrow going down, so that's position 3 to position 1, and we've ended up forming the chloride anion as a gas. Again, remember it's always gaseous. And then finally, this is our lattice formation enthalpy, and so it's the ions in the gaseous state forming 1 mole of the solid ionic compound. That's our NaCl as a solid, so that's going from 1 to 2. So then, let's say the question asks us to work out the lattice formation enthalpy. Let's say that's what we don't know. How do we actually go about calculating that value? Well, the way we do it is, again, the application of Hess's law. If we can't go a specific direction in our cycle, let's just go the other way. So we work our other way around. So in this case, we don't know what our delta H L is. And so what that means is that we can't go from 1 to 2. But instead, I could go all the other way around from 1 to 3 to 4 to 5 to 6 to 2. And so instead what I'm going to do is go that way round. If I can't go from 1 to 2, the enthalpy change will be the same. It's independent of the root, so we go the other way round. Now the key thing to remember here, like we had with the Hess's cycles, and again if you're not comfortable with those, go back to the energetics videos, was that if we had to change the direction of one of our arrows, if the direction we wanted to go was in the opposing way with our arrows, we flipped the sign of our arrow, and when we flip the direction of the arrow, we have to flip the sign of the number. So for example, this first arrow at the top going from number 1 to number 3. I want to go upwards, but my arrow is going downwards. That's not a problem, I can flip the direction of that arrow, but by doing so I have to change the actual sign of that number. So that would become positive 349. So generally, if you go with an arrow versus going against an arrow, we have to change the sign of the number. Then likewise, going from 3 to 4, I'm going against the arrow, so I would flip it. Going from 4 to 5, I'm going against the arrow, so I would flip the number. 5 to 6, again, I'm going against the arrow, so I would flip the number. And then finally, if going from 6 to 2, going from that elements in the standard states, that enthalpy change of formation, I'm going with that arrow, and so therefore that would be the sign it's already written as. And so simply like we had with Hess's law, we said that delta H1 was equal to delta H2 plus delta H3. Simply on this case, we can just add together all of our enthalpy changes. Just simply add all the numbers for the direction you've gone. So in this case, remembering to flip the sign of it if you've changed the direction. So this would be plus 349, minus 496, minus 122, minus 108, and then minus 411. And that would give your lattice enthalpy to be negative 788 kilojoules per mole. So just apply Hess's law. Remember that exothermic ones that are negative go down, endothermic ones that are positive go up, and it's always really important to have the definitions and the equations in your head for the stoichiometries. Now we can think about lattice enthalpy trends by looking at some data that has been collected. So first of all, if we look at the table on the left, what we've got here are singly positively charged and negatively charged ions. And we're just seeing how the size of these ions affects the this is for the enthalpy change of lattice formation, negative exothermic values. So for example, if I've got the lithium plus cation, fluoride minus anion, I'm thinking, what's my lattice enthalpy of formation when I take these gaseous ions and they form 1 mole of the ionic solid? And we can see that's quite big, negative 1031. If I then compare that to, say, cesium fluoride right at the bottom, that's now minus 747, so actually a smaller number, a less negative number, essentially smaller. Now, this trend also happens for any of the other columns we go down, or in fact any of the rows that we go across. And so typically what this tells us is that the bigger the ion is, the smaller this value of the lattice enthalpy is getting. Or conversely, the smaller the ions are, the more negative the lattice enthalpy is. Now sometimes you'll hear this referred to as the fact that if it's smaller, you have a larger lattice enthalpy. However, lattice enthalpy can be as we say, formation or dissociation, and sometimes using the larger number when you're talking about a negative number can be a bit confusing. By a larger number, do you mean it being more negative, or do you mean it being actually larger in terms of more to the positive side and therefore less negative? So the better way to describe it is to describe it as either being more negative or less negative. And the smaller the ion, the more negative the lattice enthalpy is. And this is simply because if you've got smaller ions, they can actually physically get closer together and interact. This lattice enthalpy comes from the electrostatic attraction of these ions coming together. And if we think about electrostatic attraction, the smaller the distance between the ions is, the greater that attraction is, and therefore the greater the lattice enthalpy, and therefore the more negative the lattice enthalpy of formation is. We can also then consider the table on the right. So again, we have this idea of size going through it, but now look, we have 2 plus and 2 negative ions. And you can see the values for these enthalpy changes of lattice formation are considerably higher. And so the second takeaway message is that the bigger the charge on the ion, again, the larger the lattice enthalpy. So the better way to say it is the bigger the charge, the more negative the lattice enthalpy. Again, the bigger the charge, that's simply just because the greater the charge, the more electrostatic attraction there is. And so if you want the most negative, actually the largest lattice enthalpy of formation, you want really small ions, but also big charges. Now the converse is true if we're thinking about lattice enthalpy of dissociations. Here we've got positive numbers if we have smaller ions and bigger charge. If we're thinking about breaking them up, that takes more energy because there's stronger electrostatic attraction for both of those factors, and so it would be a more positive number. So this is why the more positive, more negative way is probably an easy way of talking about it rather than saying a larger number. So time to have a go at some questions. So here we have the calculating values for magnesium chloride and also for calcium sulfide. So the tables that you need are there at the bottom, the magnesium chloride on the left, the calcium sulfide on the right. So have a go, pause the video, and the answers will be on the next slides. So the first question here was to calculate the lattice enthalpy lattice association, for magnesium chloride. Now, magnesium chloride is MgCl2, and so we're going to draw out our Born-Haber cycle to do this. So remember, the first thing that we're going to do is to draw on our elements and their standard states as the 0 line on this enthalpy diagram. So our elements in their standard states is magnesium as a solid, and Cl2, and the chlorine in the standard state is Cl2, as a gas. And always think about the stoichiometry. We need MgCl2, so we need to have Cl2, not a half Cl2. So the first one that I always put in is my formation enthalpy. That was the one right at the top. So that's negative 641 kilojoules per mole, and that goes down because it's an exothermic, putting energy out. So I draw that down, and that's forming MgCl2 as a solid. That's my formation enthalpy, the formation of the compound from the elements in the standard states. Then to think about making the ionic compound, I have to atomize both partners, ionize the metal, do the electron affinity for the non-metal, and then our lattice enthalpy. So atomization of magnesium first. Remember, it turns it into 1 mole of gaseous atoms. So it's magnesium solid going to magnesium gas. And it's an endothermic change, so arrow going up. Then atomize the chlorine. Now this is where we have to be really careful and think about our definitions and think about the stoichiometries. The definition of our atomization is to make 1 mole of gaseous atoms. And remember that the equation, when we had our chlorine, it was a half Cl2 making Cl as a gas. So a half Cl2 as a gas going to a Cl atom as a gas. So it makes 1 mole of our gaseous atoms. And so here, when we atomize Cl2, what we actually create is 2 Cl. We have to keep our stoichiometries. So Cl2 produces 2 chlorine atoms as a gas. But what that means is that if we have our enthalpy change of atomization for chlorine, which we're told is plus 122, we actually need 2 times that value, because we have 2 chlorine atoms now, not 1. And so this is why it's really essential to know your definitions and to know your stoichiometries from those definitions. It makes 1 mole of gaseous atoms from the definition, so we have to multiply it by 2 because we have 2 moles of chlorine atoms. Then I need to ionize my magnesium, and this has to be done in stages. So again, we can't just do twice the first ionization for magnesium, because the first ionization and second ionization are different numbers. So we do our first ionization. Remember that everything has to be gaseous, so that's magnesium plus as a gas plus an electron. And then we keep our 2Cl as a gas as the same. And then we do our second ionization to make Mg2 plus as a gas, plus 2 electrons, plus 2 chlorine atoms as a gas. Then finally, to make the chloride anions, we need to do the electron affinity. Again, remember the definitions. Our electron affinity is to make 1 mole of gaseous ions with a negative charge. Now here we have 2Cl gaseous atoms, so we're going to make 2Cl gaseous ions. And so again, because we're making 2 and the definition is for 1 mole, we have to multiply our electron affinity value by 2. And then finally, we can draw an arrow that's going to go down for our lattice formation enthalpy in this case. And then we need to actually apply Hess's law here, go one way around the cycle. We can't go the delta HL arrow because we don't know that. So instead, I'm going to go the other way around. That is going from number 1 to number 2, but going sort of the other way as opposed to that delta HL arrow. And the key thing to remember is that if you go with the direction of an arrow, you keep the sign. If you change the direction of an arrow, if you go against it, you have to flip the sign of that enthalpy change. And so I have to flip the sign of my electron affinity, so it now becomes positive 698. I then have negative 1451, negative 738, negative 244, negative 148, because these are all arrows I'm going against, and then I'm going with the arrow for the formation, so it's still negative 641. And I simply, like Hess's law, just add all those individual enthalpy changes together. So it's plus 698 plus negative 1451 plus negative 738 plus negative 244 plus negative 148 plus negative 641. And then to do this, we end up with a value here of negative 2524, 2524. But remember that the question asked us to calculate the lattice dissociation constant, not the lattice formation. Sorry, the lattice dissociation enthalpy, not the lattice formation enthalpy. And we know that lattice dissociation, to break it apart, is going to be an endothermic process. We have to take energy in to do that. So our actual answer is positive 2,524 kilojoules per mole. Always remember the unit. The question was to calculate the second electron affinity for calcium sulfide. To do this again, we need to work out our Born-Haber cycle. First thing is to put our elements down in their standard states. So that's calcium as a solid, it's a metal. And actually at room temperature and pressure, sulfur is also a solid. From there, I'm going to draw on my enthalpy change of formation, forming the compound from the elements in its standard states. So that forms the calcium sulfide ionic solid. I'm then going to put my atomization of the calcium on. So remember, that's forming 1 mole of gaseous atoms. So we just change calcium as a solid to calcium as a gas. I then need to do my atomization of sulfur. Again, the same idea. Sulfur as a solid to sulfur as a gas. These are both endothermic processes. So the arrows go up. I then need to do our first and our second ionization energies for the calcium. Again, remember, we can't just multiply the first by 2 because they're actually different processes. They're different numbers. But they are both endothermic, and you can see here that I've not drawn this to scale because the second one is, twice as high as the first one is really. But they're both endothermic, they both go up, and so we go from calcium as a gas. Remember that ionization has to happen in the gaseous state. So then we have calcium plus as a gas plus an electron. And then we go up again to calcium 2 plus as a gas plus 2 electrons, and notice that we've left the sulfur as a gas unchanged. Then we need to do our first electron affinity. So that's adding our electron to our sulfur, so we end up with the sulfur minus anion as a gas. That's an exothermic process. Remember that electron affinities, first electron affinities, are exothermic because we're putting our electron onto our, essentially it's being attracted to the positively charged nucleus. Attractive process, exothermic, arrow goes down. Then we have our second electron affinity, and this is why I was saying it was so important to know your definitions and to know whether it's exothermic or endothermic. Because remember that the second electron affinity is an endothermic process. It goes up. And this is where I see a lot of people making mistakes. They forget, they draw their second electron affinity going down. They go through their Born-Haber cycle and they end up getting the right number but the wrong sign. And in the exam that would lose you marks. And so our second electron affinity, because now we're trying to put an electron onto a negatively charged ion, that's repulsion. We have to force them together to do this, and therefore it's endothermic. We have to put energy in. So arrow goes up. And this is the one we don't know. And then finally, we always put our lattice dissociation, lattice formation, enthalpy change in. So going from that position that I've labelled 2, all the way down to the bottom of the calcium sulfide as a solid. Remember that the lattice formation is the gaseous ions forming the ionic solid. So again, we now apply Hess's law. If we don't know, if we can't go between 1 and 2, well, let's go the complete other way around. So let's go from 1, then going up the electron affinity, and then down the ionizations, and so on. So let's go the other way around due to Hess's law, because the overall enthalpy change is independent of the root. Again, remembering that if we go against an arrow, we need to flip the sign of the enthalpy change, flip the direction of the arrow, flip the sign. And so here we're going to have to go against the first electron affinity, against the second ionization, against the first ionization, against the atomizations, with the formation enthalpy, and then against the lattice formation enthalpy. And again, this is why I said it's so important to note whether in the question they give you the lattice formation enthalpy or the lattice dissociation enthalpy. In the question we were given the lattice formation enthalpy, so going down exothermic. If they'd given us the lattice dissociation enthalpy, we could have drawn our arrow going up, and therefore we would go with the sign. But because we're going against it, because it was formation, that's now positive 3030. And so using Hess's law, we just add these all together. So plus 200 plus negative 1145 plus negative 590 plus negative 279 plus negative 178 plus negative 482, and then plus positive 3030. And this gives us our answer of positive 539 kilojoules per mole, what we expect. Our second electron affinity is endothermic. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please leave a review on one of my tuition websites. I offer online tuition for chemistry, so please check those pages for prices and how to contact me. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.